In this session, we will learn about timestamp based and validation based protocols, concurrency control process of the database management system. So we already discussed about two-phase locking protocols for executing transactions concurrently. To support concurrency transactions of database management system, various schemes and techniques are there. Among them, two-phase locking protocol as well as the respective variations of 2PL were discussed in the previous session. And also how this deadlock concept can be discussed along with the two-phase locking protocol was already explained. Now, in this session, we are going to discuss about some more techniques of concurrency control of database management system. So to execute transactions simultaneously, one of the major achievement of our database management system, some more techniques were introduced, timestamp based protocols, validation protocols also. How these protocols are valid or considered to be as more efficient, and the process of insertion deletion operations are going to be supported by these operations will be discussed in this session. Now, timestamp concurrency control. Already we discussed about the two-phase locking protocol, in which we discussed about the timestamping concept of deadlocking also. But that timestamp concept as well as this protocol is different. In this example, in this technique, in this scheme, no locking is used with the timestamp concurrency control. And this is not the topic which was discussed as a timestamp method for avoiding the deadlocking. Remember that, right? So this is a new protocol based upon the time was allocated to the transactions and each data item in the read concept as well as the write concept. As before, each transaction is issued a unique timestamp indicating the time it arrived in the system actually. The size of the timestamp varies from system to system, but it must be sufficiently large to cover the transaction processing over a long period of times. Because the transactions cannot be refreshed every time, no? So very frequently it cannot be refreshed for a long period of time. In real-time applications specifically, you can say that 24 by 7 also, right? So that's why in such cases, the timestamp must be properly allocated. It must be, every system should have a sufficiently large enough timestamp allocation process actually. How these timestamps are going to be assigned? This is similar to timestamp allocation in case of long-term scheduler, as the transactions are removed from some sort of input queue actually. Timestamping is going to be, because whenever it is in queue, it will be in queue. When the transaction is entered in the processing state, then a timestamp is going to be allocated. So if the queue is empty, then we can consider as again timestamps can be, once the transaction processing which are in buffer are completed, then a new initialization of timestamp can be considered actually. So in this protocol, the transactions are going to be allocated timestamps. Not only transactions, each and every object is going to be allocated a timestamp. Of course, in case of object allocation, we may consider various levels of granularity also. Most of the time, table as well as the object means the data item will be considered, but depending upon the granularity, these timestamps have to be considered by us. And that means each object of database is associated with the timestamps. Two timestamps are going to be associated. One is read timestamp, another one is write timestamp. That is, each object is associated. Transaction is associated only one timestamp, but each object is associated with two timestamps, that is read and write timestamps actually. So with the locking, the granularity of object in the database becomes a concern here. The overhead of timestamps can be considerable if the granularity is too fine, right? So it may be a little bit overburdened, but we have to consider the timestamps depending upon the granularity, the timestamps allocation is going to be done. Each transaction is issued a timestamp. Let us assume that TA is equal to a transaction. A timestamp is allocated to TS of TA. A new transaction TJ is assigned to timestamp TS of TJ. That means the old transaction will have the timestamp value lesser than the new transaction as it is entered earlier, no? So that's why timestamp is the time at which time or at what time the transaction entered, like that we can consider. Or it may be a serial numbering, like that also you can consider, actually, right? So that's why we have to consider in case of timestamp allocation, the earlier times entered transactions will get the lower timestamps comparing with the transaction entered later, actually. So that's why TJ entered later than TI. So that's why timestamp of TI is less than timestamp of TJ. Such a way, the timestamp must be allocated. And this protocol manages concurrent execution such that timestamps determine the serializability order. So we need not explicitly check serializability or not, or we need not consider any precedence graph, etc. But we will anyway compare it, actually the end of this session. And the protocol automatically manages the concurrent execution of transactions, which automatically based upon these timestamps, it will determine the serializability order, actually. In order to assure such behavior, the protocol maintains for each data queue two timestamps, as I discussed, represented by write timestamp of queue and read timestamp of queue. How to allocate first? Write timestamp of queue is allocated. It is the largest timestamp of any transaction that executed write queue successfully. So, which transaction has executed write queue? The respective transaction timestamp will be the write timestamp of that objective. Similarly, read timestamp, the largest timestamp of any transaction, that is the transaction which is having the largest timestamp. Timestamp means recently entered, in other words, that executed read queue successfully, that timestamp is going to be allocated to our data item queue, actually. Such a way, we are going to consider the respective data item is going to be processed and the respective data item are allocated various timestamps, actually. These timestamp based protocol is an ordering protocol which ensures that any conflict between read and write operations are executed based upon their timestamp order. So how this is going to be considered? Let us assume that if a transaction TI issues a read queue, right? So in such cases, TI issues a read queue means when it is going to be allocated, when the read is going to be acceptable read. If the timestamp of TI is less than the write timestamp of queue, that is already each object is associated with one read timestamp as well as one write timestamp. So if already some write timestamp is there for that particular queue, if the current transaction timestamp is less than the object's write timestamp, then TI need to read a value of queue which is already overwritten. That means it's supposed to read, which is overwritten. Which is overwritten means whether that particular transaction might be completed or not, we don't know that. That's why what we supposed to consider, this read is supposed to be rejected. Why? Because it was already written by some other transaction. Whether that particular transaction was completed or not, we do. Because if it is completed, it won't be there, no, anyway. So that's why in such cases, the read operation is going to be rejected as TI is rolled back. Hope you are getting. Reading an object which is already updated by some other transaction is not acceptable, no? So such a way that conflict read write is going to be considered here. And the second one, if the timestamp of TA is greater than write timestamp of Q, then the read operation is executed. Because the current timestamp is more than the write means automatically this is a newer transaction which is timestamp, and the queue was updated by the transactions which are earlier actually. Read operation is executed and our timestamp of queue is going to be updated. It will be updated because the current timestamp it has to be updated. So while updation, it will check maximum of read timestamp and TS of TI. Whichever is maximum, that value is going to be updated. Anyway, this is condition is satisfied means it may be greater than or it may be equal to also. So that's why in such cases, we are going to consider the read is going to be acceptable. And similarly, if you are going to, any transaction has to be executed write queue, when the write queue is going to be followed or not, whether the write queue is going to be supported by the timestamp or not, that will be based upon the following two conditions. So what are those three conditions here? Timestamp of the current transaction is less than the read timestamp of queue, because already less than means which was already read by that particular one of the earlier transactions. Then what happens? Already read by some other transaction means we cannot update, no? So that's why the value of queue that TI is producing was needed previously, and the system assumed that the value would never be produced. That is, write cannot be updatable. So then what we supposed to do? Hence, write operation is going to be rejected. TI is going to be rolled back actually. That is the first one. That is, we would like to write an data item which is already read by the earlier transactions. Timestamp of TI is less than our timestamp of Q means which was read by already existing transaction, earlier transactions which entered into the system. So that's why already they are processing now. So once we are going to update, then what happens? The problem may be conflict may be occurring. Because of that, the inconsistency may arise actually. So that's why if any TS of TI is less than write timestamp of Q, then TI is attempting to write an obsolete value of Q. That means the timestamp of current transaction is less than the write timestamp of Q means here, which was updated by earlier transactions and which is going to be, we are overwriting again, we are updating again. So that's why whether the already updated transactions were considered to be as confirmed or not, and that's why committed or not, that's why the current write operation is going to be rejected. TI is going to be rolled back. Otherwise, write operation is executed and the write timestamp of Q is going to be updated based upon the current transaction timestamp actually. So, in summary, write timestamp is going to be of a transaction is going to be get executed if the current transaction timestamp is going to be less than, not less than the read timestamp of Q and not less than write timestamp of Q. In both cases, it must be read timestamp of Q and write timestamp of Q must be greater than the current transactions. Then only this updation is going to be valid actually. So the write operation is executed and the write timestamp of Q is going to be set to the value of the current transaction actually. The same was represented by a pseudocode actually. Read transaction TX performs read the object. If transaction T of X is less than A, already WTS means existing write transaction of the timestamp of write timestamp. WTS stands for object, then roll back. As I told you, which is timestamp of the current transaction is less than the write timestamp of the object, it must be rolled back. Otherwise, TY can be issued. That is, transaction TY is younger than TX. So that's why if the TS of transaction is greater than write timestamp of object, execute read object, and we have to set to the maximum value actually. So similarly for write, which I already explained to you, timestamp of the current transaction is less than the read timestamp, then roll back. Timestamp of current transaction is less than the write timestamp of object, then also ignore that particular write option, that is roll back again. Otherwise only execute write timestamp, set the right timestamp of an object with the current transaction actually. Right? Now, if you consider this example here, T1, T2, T3, T4, T5 are the objects. Let us assume that these are entered into the same order. That is, timestamp of T1 is lesser than the timestamp of T2, lesser than timestamp of T3, lesser than timestamp of T4, lesser than the timestamp of T5. Right? So that means these are entered in the same order. So T1, then T2, then T3, then T4, then T5. So this timestamp is going to be lesser than, and timestamp is lesser because recently. So what is the first? First statement was here according to this read X. Read X means here X is allocated timestamp. Let us assume that this is the order of 1, 2, 3, 4, 5. We have the variables X, Y, Z. So if each element will have read and write, read and write, and read and write. Right? So let us assume that read of X means first was initially everything is 0. This is 0, this is 0, and all are zeros. Read X means 0 is there, but T5 is reading, so it is updated with the T5 initial value. Then next read Y of T2. So Y is going to be allocated, read of object Y is going to be updated with the T2 transaction. Let us assume that it is 2. Fine. And third instruction is read Y. Which transaction is reading? T1. Right? So T1 is read Y. What is the value of time transaction of T1? T1 time transaction is less than the already read transaction of Y. So we can update it. We can update means T1 is acceptable. But what is the timestamp of read timestamp of Y? 2 only, because our current transaction is 1. So which is lesser, one maximum value we have to update now. So that's why. Fine. Then write Y. Write Y is by 3. So that's why Y write operation, so that its timestamp is updated with the respective transaction as 3. Write Z next one. So Z is also updated with 3 next to transaction. Okay. So next instruction is read Z. What is read Z here? By 5 actually. So when you are considering this read Z next to transaction, and the current transaction is 5, and read Z is as having 0, so that's why it is updated with 5 only. Fine. Next, after that again one more read Z is there, but transaction 2. But its timestamp is lesser than the already existing timestamp. So you can consider it. But what happens? Its timestamp is read Z means read Z timestamp is 5, but the current transaction timestamp is 2, then it will be aborted. Why? Because this read is not going to be allowed. Its time slot is lesser than the Z already existing read Z. So that's why it cannot be processed. Aborted means rolled back actually. We'll go to the next one, read X. Read X means X. X is having reading as a 5. Right? So again here also we are having lesser than, can be aborted. T3 also, write W, aborted, because read W is by 4 first. Then read transaction time complex is timestamp is lesser than the write timestamp of the W. Then automatically this is 3. So 3 is lesser than the 4. So we cannot update. It can be aborted. Like this process is going to be considered whenever the timestamps are going to be allocated. You have to consider the respective read timestamp and write timestamps of the respective objects, and the current transaction must be checked. Whichever is going to be acceptable, those timestamps are going to be allowed. Otherwise, the respective transactions are going to be respectively rolled back actually. Right? So we will see one more example, and the next example is a little bit more detailed way. Timestamp ordering protocol. We have 3 transactions in this example. You observe. So T1, T2, T3. So three transactions are there and three objects are there ABC. Right? So whenever the instructions are executing, we are writing here action is there. Action means whether we are whatever the protocols or conditions we explained in the previous slide, based upon those conditions, whether acceptable or not, that we will check. If it is not acceptable, we will consider it as a abort or ignore can be considered. Now, T1 is going to be allocated, T2 is going to be allocated, T3 is going to be allocated with the timestamp as a 200, 150, 175. That means T2 is older, and next T3, next T1 are entered into our system, in other words, you can say. Now, so when they enter here, the first one is read B. Initially ABC are having, these are the initial values, 0, 0, 0, 0, 0, 0. Read B. Read me means by which transaction? T1 transaction. So timestamp of T1 is greater than or equal to already existing respective right timestamp of the B or not, we have to check first. So read B means here, read is by T1. What is its timestamp? 200. So 200 is greater than or equal to right timestamp of B means it is 0 initially. So that's why yes, then okay. That means read operation is okay. Read operation is okay means acceptable. When it is acceptable, it has to be updated, no, depending upon the maximum value. So our read timestamp of B is updated as a 200 because existing read timestamp of B is 0 and the current transaction timestamp is 200, which is maximum. Current transaction 200 is maximum. That with that RTS is updated. RTS means read timestamp of B. Okay, fine. Next, second instruction, read A. In A also same logic. Second instruction by times transaction T2, that is 150. So if it is 150, 150 is greater than right timestamp of A, then automatically A is going to be acceptable. Same logic, like B was reading and initially 0 is there. For right of A is also initially 0. The current transaction timestamp is 150. 150 is greater than or equal to greater than right timestamp of A already existing value 0. So that's why it is acceptable. Read C. Same reasoning. Read C also. Timestamp of T3 is 175 and right timestamp of C is 0. So it is updated. Up to this same logic. And we are coming to the right. Fourth instruction. Write B. Write B is for by which transaction? T1 transaction. So T1 transaction, TS of T1 is 200 actually, which is greater than or equal to, we have to check with the right timestamp of B first, then read timestamp of B. Right timestamp of B is, what is the value of right timestamp of B? And 0. So that's why it is okay. We are updating. Right? So even if you are considering it, read timestamp also, it is greater than or equal to, then also it will be updated actually. Then the next one is write A. In case of write A also, what is the transaction? T1. T1 is 200 and write timestamp transaction of T1 is 200 is greater than right timestamp of A, that is 0. So that's why we are updating here. Right? And the third one, sixth one, instruction is W. Write C. Write C by which operation? T2. So we have to check TS of T2. TS of T2 is 150 here. So 150 is less than RTS of C. That is read transaction of C, write transaction of C. Read transaction of C, it is going to be considered as a 175, which is lesser, doesn't satisfy, it is lesser. So that's why we have to abort. Of course, write it satisfied, but this read is not satisfied. Both must be satisfied. So we are aborting T2 means T2 must be rolled back actually. Next, write A. Here also in this case, write A if you are considering, TS of T3 is 175, and we have to check with the read timestamp of A, write timestamp of A. What is read timestamp of A? 150. Fine. TS of T3 is greater than read timestamp of 150. So that's why need not be aborted. But what is second condition? With write timestamp also I have to check. But TS of T3 is less than the write timestamp of A. So that's why we have to ignore it actually. We need not abort. So after this status, we are having read timestamp is 150, write timestamp is 200 for A, and for B, read timestamp is 200 and write timestamp is 200. For C, read timestamp is 175, write timestamp is 0. Like this process is going to be continued. An algorithm is going to be, or a program is going to be right for this timestamp ordering protocol, so that what happens, the conflict between read and write statements can be avoidable and the serializability will be assured in case of timestamp ordering protocol. So logs, overhead of the allocation of the logs and overhead of the respective management of the logs, these things are need not be considered. Only allocation of the timestamp is going to be considered here, and based upon the timestamps, the respective process is going to be allocated by us. Now we will compare with these things and correctness of the timestamp protocol. The timestamp ordering protocol guarantees serializability. How? Precedence graph. Transaction with smaller timestamps for first executed, then the transaction with a larger timestamps are executed. That means the right statements of right statement is going to be, which is already entered, which is already read by the smaller timestamps are going to be, then only the larger timestamps are. That is, since all the arcs in the precedence graph will be of this form only. Smaller timestamp transactions are connected with the larger timestamp transactions with a precedence of arrow actually. There will be no cycles because of this and the precedence graph, and timestamp protocol ensures freedom from the deadlock as no transaction ever waits. It is not waiting, just you observe the previous discussion. If it is not satisfied, we are aborting, that's all. We are not waiting, releasing of the logs are like that. No, so no waiting means no deadlock concept of actually. But the schedule may not be cascade free and may not be even recoverable, because already we aborted means we can recover or we can consider to be as again restart process is going to be considered. So based upon that, cascading of rollbacks are going to be, possibility is there. So that's why these two are not these two, recoverability as well as cascadeless schedules, are not possible with this timestamp based protocol actually. So recoverability and cascade free problem with the timestamp ordering protocols are these two. Suppose TI aborts, but TJ has read the data item written by TI. It is possible, no, depending upon the timestamp processing, then TJ must also be aborted. TJ has been allowed to commit earlier, then the schedule is not recoverable. So this is the problem with this, because we are not checking whether it is dependency is there or not actually. Any transactions that has read a data item written by TJ must abort. This can lead to cascading rollback. A chain of rollbacks are going to be possible in such cases actually. So let's see what are the solutions. Various solutions can be considered, but some of the solution, a transaction is structured such that its writes are all performed at the end of the processing, as one of the variations of our two-phase locking protocol, no, similar to that only here also. So a transaction is structured such that all its writes are going to be performed at the end of the processing, and all writes of the transactions form an atomic action. No transaction may execute while transaction is being written. That means atomic means only, we already defined the definition of atomicity at the time of defining transactions. As it executes alone itself independently, right? So that's why all whenever a block of write statements are executed by a transaction, then all other transactions are going to be stopped so that no transaction may execute. So a period of time till these returns are executed, then possibilities considered, cascadeless can be considered. A transaction that aborts is restarted with a new timestamp. Because if it is old timestamp, the same process is going to be, or same type of restarting, the same type of aborting the transaction is possible. So that's why whenever a transaction is aborted, it has to start with a new timestamp. So that what happens, it is a recent transaction. Then the possibility of the repeated aborting the transaction cases can be avoidable by us. And limited form of locking actually. And second solution, instead of using a total locking system, we may combine these two timestamp protocol based protocol as well as the locking system. Wait for data to be committed before reading it actually. So any transaction is reading, we have to wait before it is going to be committed by the transaction which is already written or which already executed write statement actually. This is one of the solution. Wait for some time. And solution 3 is use commit dependencies to ensure the recoverability. These are all various solutions are suggested actually, but some solution was suggested which is known as a Thomas Wright rule actually. In timestamp ordering protocol, when timestamp of a transaction attempting to write an object is less than the write timestamp of object of concern, then the write is simply ignored. If you observe this or if you follow this rule, then the cascading rollbacks can be a little bit avoidable actually. This is known as Thomas Wright rule. So this Thomas Wright rule is going to be discussed now, so that a modified version of the timestamp ordering protocol in which obsolete write operations may be ignored under certain some circumstances. So that what happens, this cascading of the rollbacks are we can consider it as a once aborted dependency transactions or which are already modified transactions need not be aborted, right? So a continuous dependency rollbacks can be or avoidable here actually. When a transaction TI is attempts to write a data item Q, if transaction respective transaction timestamp is less than the write timestamp of Q, then TA is attempting to write an obsolete value of Q. Rather than rolling back, we will ignore it. Rolling back means whichever the transactions are already depends upon this transaction again must be rolled back, which results cascading. Some of the transactions are already committed, then rollback is not possible also. So that's why irrecoverable transactions will be possible. To avoid these things, we will consider this Thomas Wright rule, in which case the transaction timestamp is less than the W timestamp of the respective object. Then instead of attempting to write the obsolete value, we have to instead of rollbacking, we will attempt to write an obsolete value. No, so that's why we will ignore it actually. So rather than rolling back, the timestamp ordering protocol would have done this write operation can be ignored. Otherwise, this protocol is same as the timestamp protocol. That is, in the second case, wherever we are considering it as an abort operation is considered, instead of aborting, we may consider it as a ignore. Thomas Wright rule allows greater potential concurrency. Because of this, the concurrency is more allowed as well as the recoverability or irrecoverable transaction or cascading rollbacks are also going to be reduced actually. View serializable schedules that are not conflict serializable can be considered by us actually. Okay. So by using Thomas rule, this timestamp based protocol can be further processed effectively. The execution of concurrent execution of the protocols, another scheme is there, another technique is there, we will call it as a validation based protocol. protocols. This validation based protocol is also used to execute our transactions concurrently, avoiding the problems which are faced because of this concurrency. Execution of transaction TI is done in three phases in these validation based protocols: read and execution phase, validation phase, and write phase. One more phase was introduced here actually. What is read and execution phase? Transaction TI writes only to temporary local variables. Transaction TI is writes only temporary local variables. That means whenever any updations are there, those are going to be written only in the local variables, not in the database variable actually. Temporary variables. Validation phase means the transaction TI performs a validation test to determine if the local variables can be returned without violating the serializability. That is the second phase was introduced, in which the validation process is going to be considered actually. That means a transaction TI performs a validation test to determine if the local variables can be returned without violating serializability. Maybe at a time it can be done actually. Write phase means if TI is validated and the updates are applied to the database, otherwise TI is going to be rolled back. So that's why this validation phase itself decides whether the particular transaction has to be committed further or the transaction has to be rolled back actually. The three phases of concurrency executing the transactions can be interleaved, but each transaction must go through these three phases in that order only. That means all transactions need not be in the read phase, all transactions need not be in the validation phase at a time. Each transaction must have interleave of these phases can be considered depending upon the transaction entering and the processing and time taken to do the process, etc. But each transaction should always consider this type of assumption, this type of three phases must be executed or undergo these three phases in the same order actually. Assume for simplicity that the validation and write phase occur together atomically and serially. This process is going to be depending upon the validation process can be considered actually. This validation protocol, the transaction T1 has three timestamps here in this example, in this validation based protocol: start timestamp, validation timestamp, and finish timestamp. The time when the TI started its execution, it's a start timestamp. The time when TI entered into the validation phase is a validation timestamp, and finish means the time when the TI is finished its write phases. Then write phase and update all values, local variables into database. Then it is finished. The serializability order is determined by the timestamp given at validation time. This is done to increase the concurrency. So why we are allocating? Because it is considered to be as having a validation phase. It will check whether that particular order of timestamps and processing of timestamps are proper or not, so that the serializability can be properly determined here. This protocol useful to very useful and gives greater degree of concurrency if the probability of the conflicts is low. So if the probability of conflict is low, then this protocol is effectively supports the degree of a higher degree of the concurrency of the transactions. The serializability order is not pre-decided and relatively few transactions will have to be rolled back. This validation based protocol is more suitable actually. If for all TIs with the TS of TI is less than TS of TJ, either one of the following conditions are going to be considered. That is, the timestamp of TI is less than timestamp of TJ, one of the conditions must be held. Finish of TI must be less than start of TJ. That is, before starting the next one, the first one, updations must be finished. Start of TJ must be less than finish of TI. That is, once it is started and the finish of TJ must be always considered to be as a after completion of the starting and less than validation of TJ. That means either of these two conditions must be hold. That is, before starting the TJ, the first one must be right phase must be completed, or if it started, the timestamp of the TJ must be less than the finish of TI and less than the validation of TJ. That means the finish of TI must be after validation only. Before validation, we are going to consider. The data items written by the TI does not intersect with the set of the data items read by the TJ. For that purpose only, that is conflict between read and write is going to be solved by using this constraint actually. That is, when the transaction started and the transaction TI is finished, that if it is finishing after it starts, before finishing and validation, after starting, the finish must be continued. That is, validation of the second transaction must be allowed after finishing the first transaction. Because of this, the conflict read write can be avoidable. Validation is succeeds and TJ can be committed. Otherwise, validation fails, TJ is aborted. Otherwise, what happens? Dependency will be there. Then cascading rollbacks must be considered actually. Why? Because either the first condition is satisfied and there is no overlapped execution. Just now I explained to you. Or if the second condition is satisfied, then the writes of TJ do not affect the reads of TI. Because validation is done after finishing the first one, no? So that's why based upon that. So since they occur after a TI has finished its reads, and the writes of TI do not affect the read of TJ, since TJ does not read any item written by TI, because validation is going to be done after completion of this finish. These are the schedules produced by using validation. Let us assume that two transactions are there, read B, and the second transaction is read B, updation of B, read A, updation of A. Read A, validate, we have to validate because we are considering the read was done by the already 26. Display A plus B. Then here also we have to validate that. Now please observe that when T25 entered earlier and finished earlier, T26 entered later, it is possible, but the validation has been done after finishing the T25. So this is entered start time and this is the start time of this is going to be, this is started S1, let us assume that this is started at S2, right, start time. And here this is the validation time and this is the completion time actually, finish time. But here validation time is V2, this is F2. You observe here. Our S1 is, S2 is, S1 is less than S2. So first condition doesn't satisfy. Because S2 entered after S1 only. But remember here, it finishes, after finishing only, the second transaction validation is considered. So that's why the validation protocol makes this conflict read writes are going to be avoidable by using, by ensuring serializability. Right? So this is the comparison between timestamp based protocol and two-phase locking protocol. Waiting stage, two-phase locking protocol, transactions are put in waiting stage, and timestamp protocol, transactions are killed and restarted. Serialization order, 2PL is determined by the conflicts and TS is determined by the timestamps. Serializability, need to wait for commit by other transaction, 2PL, solved by the strong strict 2PL protocol. In case of TS, buffering of write actions, that is waiting for write operations of the transaction can be used. Deadlocking, 2PL, risk of deadlocking is there, but TS is deadlocking is less probable actually. And also, timestamp based method is superior when transactions are read only or when the concurrent transactions are rarely write the same element actually. Two-phase locking protocol is superior when the number of conflicts is high because the locking is going to be having delayed transactions and may cause the deadlock actually. And the probability of rollbacking is also higher in case of two-phase locking protocol, in case of timestamp based method, and this causes greater global delay in the system actually. Right? So based upon the methods, this causes greater global delay. The following and we have a indicated by timestamp denotes the set of schedules generated by timestamp based scheduler, where all actions ignored by the Thomas rule and all actions are rolled back, transactions are. And we discussed already about the multi versions and the multi versions of concurrent transactions. Data items updated at various levels based upon the multi versions was discussed at the time of two-phase locking protocol itself. And the same multi-version concept is applicable to timestamp based protocol also. And the material is taken from both prescribed textbooks, that is Koth and Navadip. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.